Hello, ECEG 431. Welcome to Project 3. I think I have all this set up. I am recording this before I travel, so a little bit of technology interestingness. But today I'd like to introduce Project 3, let you know what you're working on that. So as is the norm, you can find everything you need on the project website, on the Moodle. I have some items as well as the majority of the stuff on the Project 3 at the Nando Tetris, so just go there. But we're going to be talking about memory and sequential logic. Unfortunately, I don't have any reading notes yet to clear up, so if you have any, let me know. But as those come in, I'm sure you will have some as you're reading and looking and seeing how this connects. But as an overview, you have now built up a set of basic gates. We've now combined those into forming a basic ALU. And what we're going to do for this project is enter the world of sequential logic. And we now have time as a variable to play with. So now say we have time, what that means. That implies a history. There's things before, things after. So there's this history of getting up to the point we are now. And that also kind of implies some idea of remembering something. There's a path going through there. So time means remembering things. So we add time into our logic, what we get is memory, and that's what we're going to be building. So at this point in the course, you have used a huge chunk of everything you've learned in ECEG 241, your digital logic course. We've gone all the way up from gates up to building an ALU. You're able to do processing. Now you can add, you can subtract, you can start doing logical negation, ORing, etc. You can do all that just with gates that you have made. So now what we're going to do is start architecting this so everything comes together and we can build a genuine CPU, or central processing unit. They're really the core and brains of the computer. So if we kind of look where we are on the map, we can see we have started over here with our NAND gates. We built up basic gates, up into algebraic logic gates, combined those together to form an ALU, and then right around here, we're starting to work on the actual CPU, and there are two components. We're going to build up the ALU, which you have, and there is the RAM, and that's what we're going to work on in this class, building up the random access memory, which is going to let us then actually build the computer. So start zooming in on what we're doing. Up to this point, we've ignored time. We haven't thought much about it. We've just kind of said circuits work. And in fact, that's how combinational circuits work. There is no sense of time. You simply give the inputs. The outputs are there. It doesn't matter what any set of previous inputs were. If you had a 0 before, now you have an input of a logic 1. It doesn't matter. The NOT gate's just going to invert. It doesn't care. When we add time, that is no longer the case. If we really zoom in on the chips themselves, and you would see this maybe in a circuits class or a digital logic class, you start looking at the labs, but these chips don't flip instantly. There is still a time that it takes for them to change their value. And when you really get into really serious chip design, looking at trying to get billions and billions of these transistors all formed together on a single wafer, they all have to work in harmony. They all have to kind of work together, and such that if you read a value, you can guarantee it's at the value it's supposed to be. It's not in a transition phase. And that's a huge, huge chunk of chip engineering and design, is guaranteeing and verifying that all the paths and everything work out. Let me show you what I mean, since it might be a little confusing. I think it's the next one coming up. So pause that thought. Before I get there, I think when I start talking about why time is important for variables, let's look at that. In code, we might say x equals 17, then later in a loop, we might say for I in range 0 to 10, print I. So if we have a variable, by its very name, variable, it means it's going to vary. It means it's going to change. And so depending on when we look at that variable, it is going to be different. So in this little chunk of code, anytime after we assign 17 to the variable x, if we read it, it's going to be 17. But look at I. I is going to be a different value if we read I, depending on how far in that loop we are, because I is changing. And we just, in the code, want to make sure that when we ask the CPU to tell us the value of I, that we get it at a point where it is not in the middle of a change, it is set. So all the work in the software is done assuming that when we increment something, it's going to increment and be set, and we don't have to worry about it. So the big idea, and even in this loop kind of way we think about it, is that we want to break time out, this continuous time, into discrete moments that we look at things. And we don't really then care about what's going on in between, just in those moments when we would sample or observe. And so what that means, we call that discrete time. Time we care about, and especially in digital systems, time in discrete moments and not on a continuous spectrum. So here's where I think this might make sense. This is a timing diagram for a chip. You can think of this however you want, but essentially there's some input going to a chip, a gate of some sort. It's going to then respond and then go show its output. So our abstraction has been that a NOT gate, if we set an input of 0, the output is 1. And so we set 0, we read the 1. We set a 1, we read the 0. What happens though, if you change, you go from 0 changing to a 1, we expect the output to change from a 1 to a 0 accordingly. But it's that in between. If we zoom in on that time, this is what it starts to look like. So if you look kind of over, I'm looking kind of right here. If we start going over, if we would read the time right around this 2 nanoseconds, that's going to be pretty stable. We can see at that point there is always going to be at a low voltage. And then likewise around this 4 nanoseconds, it's pretty much always going to be a nice solid high volt. So those are what we call stable. At that point in time, around 2 and 4 nanoseconds, everything is stable, and that's when we're fine to read our signals. But where it gets tricky is, I'll do it in yellow, this area right around there. You can kind of see, especially right there, how it's kind of, there's a lot of little lines happening. And if we put read at this point in time, depending on the particular path it's taken or whatever's going on in the circuit, it's unclear if we're going to get a low voltage or a high voltage. And so what we want to do is that we do not want to read the circuit at those points in time. We only want to read it when it's stable. And that's why it takes a lot of engineering to make sure that we can get really these discrete time components and only look at things when they are stable. Let me pause it there. That's kind of the brief intro to time in circuits. So this is a big chunk of what a lot of hardware designers take time doing, is ensuring that every piece of hardware is only looking when things are stable, not when they're transitioning. For us, I will tell you, it's going to be a little bit easier. So a lot of that engineering is taken care of, and now we get to focus on the next level of just looking at memory. So I'll stop this one now, and I will come back in a moment for the rest of it.